Hello friends, welcome to my YouTube channel. Now, yesterday I told about phase transition and there are two type of phase transitions that I told, and I also discuss about first order phase transition, its examples, and there we see that first order phase transition obey first latent heat equation or Clausius-Clapeyron equation, and we also derive it. Okay, now in today's lecture I shall going to discuss the another type of phase transition which is called second order phase transition. Okay, second order phase transition. Okay, second order phase transition. Now what is second order phase transition and what are the basic properties of second order phase transition? Here the in first order phase transition what happened, entropy and volume changes, but here entropy and volume remains constant. In second order phase transition, entropy and volume remains constant. Okay. Now we see that in first order phase transition obey first latent heat equation or Clausius-Clapeyron equation. Similarly, second order phase transition, second order phase transition satisfies Ehrenfest equation. Ehrenfest equation. Okay. Now in first order phase transition we see that Gibbs potential changes continuously and its first order derivative changes discontinuously, that we saw in first order phase transition, but in second order phase transition Gibbs potential and its first order derivatives both changes continuously, both changes continuously, but second order derivatives changes discontinuously. Okay, discontinuously, that is Gibbs potential and its first order derivatives changes continuously, and but second order derivatives changes discontinuously. How we can explain it? So let's see by graph. Okay, now so if we draw a Gibbs potential temperature curve for second order phase transition, here this is G and this is temperature T and this is the transition line. This is initial phase, this is final phase, say. So the Gibbs potential changes continuously, that means this. So there is a continuity at the transition point, there is a continuity at the transition point. Okay, so this happens for first order phase transition, second order phase transition. So this is the curve for Gibbs potential and temperature for second order phase transition. Okay, second order phase transition. And if we look back the first order derivative versus temperature curve, then what it looks like, we know simply dg equals to vdp minus sdt, that we know. So here del g del p temperature constant is v and del g del t pressure constant will be minus s. So if we draw the first order derivatives with respect to temperature, okay, say this is temperature and take any derivative, first order derivative, that is del g del p and suppose this is the transition line, this is initial phase, this is final phase, then it will also continuous. Okay, it will also continuous. Okay, this happens for second order phase transition. But in first order phase transition, what we saw that there gives potential or changes with temperature continuously. That means Gibbs potential temperature curve will be same for both first order and second order phase transition. Okay, but in second order phase transition, first order derivatives of g changes continuously, but in first order derivatives, what we get? We found a discontinuity. That is, if we draw it, we found a discontinuity. Okay, like this. Okay, so there is a discontinuity at the transition point. So you have to remember that in case of a first order phase transition, Gibbs potential changes continuously. Okay, and its first order derivatives changes discontinuously. But in case of a second order phase transition, Gibbs potential and its first order derivatives changes continuously, while second order derivatives changes discontinuously. Okay, so you must have to remember. Okay, now what are the basic examples of second order phase transition? Okay, what are the basic examples of second order phase transition? The familiar examples of second order phase transition is, say, example. So just take one, that is the transition from ferromagnetic substance to a paramagnetic at Curie point. We know that Curie temperature is a temperature at which a ferromagnetic substance becomes paramagnetic. So we can easily conclude that transition of ferromagnetic substance, transition of ferromagnetic substance to paramagnetic, to paramagnetic at, say, Curie point. Okay, so this is one example, that is transition of ferromagnetic substance to paramagnetic. This is at Curie point. Okay, we know that Curie temperature is the temperature at which a ferromagnetic substance becomes paramagnetic. Okay, now let us take in another example, that is conversion of liquid helium 1 into 2 at lambda point. Okay, we will study it later. Liquid helium 1 to helium 2 at lambda point. Okay, at lambda point, that is approximately 2.19 Kelvin. Okay, that is transition of liquid helium 1 that we will learn in superconductivity. Transition of liquid helium 1 to liquid helium 2 at lambda point. These are the examples of second order phase transition, and also you can see the order disorder transitions found in chemical compounds. Okay, order disorder transitions, order disorder transitions in, say, chemical compounds, in chemical compounds. These are the example of second order phase transition. Okay, fine. Now I told that second order phase transition is governed by Ehrenfest equation, and that equation we already derive in Maxwell's relation chapter. But for your but for but since I am doing here the phase transition, I must also have to do again it. Okay, so since I am talking about Ehrenfest equation, I also derive it in this chapter. I also did it by using Maxwell's relation in the previous chapter. Now I will also going to do it again. Okay, so just see what are the Ehrenfest equation, okay, of second order phase transition. Okay, we know that in second order phase transition entropy and volume remains constant. So let us assume the constancy of entropy at first. We assume the constancy of entropy. Okay, and we take entropy as a function of pressure and temperature. Okay, at first we assume the constancy of entropy and assume entropy as a function of pressure and temperature. Now what will be my ds? My ds will be del s del p temperature constant dp plus del s del t pressure constant dt. Okay, now what we can write from Maxwell's relation, del S del P temperature constant means minus del V del T pressure constant, and this we can write as T into 1 by T, del S del T pressure constant dt. Now again volume expansion coefficient can be written as increase in volume per unit rising temperature. Okay, increase in volume per unit rising temperature. So from which del V del T pressure constant can be written as minus V alpha dP plus this is simply T del S del Q del T pressure constant, that means Cp. So this is the relation. Okay, so we can write Cp dt upon T minus V alpha dP. Okay, now we found this. Now what I can say now? Now I can say that in second order phase transition entropy does not change. That means entropy remains constant. So we can write the initial phase entropy equal to final state entropy. So what we can write? We can write ds1 this equals to ds2. So substitute this value. So in case of first phase Cp becomes Cp1 and this is simply dt by t, and since volume remains constant it would become V, it would remains V, alpha becomes alpha 1. Okay, and here for second order second phase it becomes this. Okay, minus V alpha 2 dP. Okay, fine. Now if we take dt upon t common, so what we get? We get Cp2 minus Cp1. This must be equal to, you take vdp common, so it will become alpha 2 minus alpha 1. Okay, so what will be my dp dt? What will be my dp dt s constant? My dp dt s constant becomes this. So Cp2 minus Cp1 by T V alpha 2 minus alpha 1. Okay, so this gives a name 1. So by assuming the constancy of entropy we arrive at this equation. Okay, so now let us check. Okay, let us check the constancy of volume and see what we arrive. Okay, so let us consider the constancy of volume. Okay, so now here we assume the constancy of volume, constancy of V, and we assume V as a function of again P and T. Okay, V we assume P and T. So since dV is a perfect differential, what we can write? Del V del P temperature constant dP, this is del V del T pressure constant dt. Okay, now this can be written as V1 by V del V del P T dP plus V1 by V, this is simply del V del T pressure constant dt. Now what is this? We know isothermal elasticity. This can be written as minus V del P del V temperature constant. So its reciprocal will be compressibility, that means minus 1 by V del V del Pt. This term is known as compressibility factor. So this term is compressibility factor provided by minus sign, that means V Kt dP. And this term is alpha, that is volume expansion coefficient, that is V alpha dt. Okay, so dV can be written in this way. Okay, now we apply the condition that in second order phase transition volume remains constant, so V1 equals to V2, that means what we can write, dV1 equal to dV2. So if we substitute this, so V alpha becomes alpha 1, this is dt, this is minus V kt1 dP, and this is simply V alpha 2 dt minus V kt2 dP. Okay, V dt common, so this is alpha 2 minus alpha 1, and this is V dP kt2 minus kt1, and this is what, this is dP dt volume constant. Okay, dP dt volume constant, this will be what, alpha 2 minus alpha 1 divided by kt2 minus kt1. Okay, so this gives a name 1. So equation 1 and 2, equation 1 means that I write previously, these are known as the well-known Ehrenfest equation, so I write it again. Okay, so these two equations are known as the well-known Ehrenfest equations. Okay, I write it again, that is dP dt is constant, you can write as Cp2 minus Cp1 by dV alpha 2 minus alpha 1 and dP dt volume constant. Okay, that you can write as alpha 2 minus alpha 1 by kt2 minus kt1. Okay, so here Cp are the specific heats at constant pressure, alpha is the volume expansion coefficient, and Kt is the compressibility factor. Okay, so this is what about today. So dear guys, if you don't subscribe my channel, then kindly subscribe my channel to get latest videos on physics. Okay, thank you.